Hello friends, up till now we have completed the thermodynamics of the isothermal process, the isobaric process, isochoric process and also the adiabatic process. And now we have come to the last part of this chapter, thermodynamics. Last 2 points are remaining, that is the cyclic process we are going to discuss in this lecture. Now cyclic, according to the name suggests, like a cycle, like that is the system which is supposing at state A, it comes to state B, but again it comes to state B, but again it goes to its initial state A. So such process where the system again comes to its initial state, returns to its initial state, is a cyclic process. Now, in this process, the change in the internal energy is zero. Now, according to first law of thermodynamics, we have Q is equal to delta U plus W. Now here delta U is equal to 0. So for a cyclic process, Q is equal to W. That is, whatever the energy is given, it is all used to do the work. This is the PV diagram for the cyclic process. The y-axis is the pressure, x-axis is the volume, and the system, though the system changes, it moves from one state to other, but at the end, it returns to its original state. So such process is called as a cyclic process. The working of all heat engines is the example of a cyclic process. Next point which we would be discussing is the last point of this chapter which we would be discussing now is the free expansion. Now, the free expansion is the adiabatic expansion, where there is no exchange of heat with the surrounding. Heat is neither given to the surrounding nor it is taken from the surrounding. And hence, Q is equal to 0. Also, the free expansion is such that no work is done. No work is done by the system, no work is done on the system. So, W is equal to 0. And hence, now from the first law of thermodynamics, we have Q is equal to delta U plus W. Now since Q is equal to 0, W is equal to 0. So delta U is equal to 0. Now this free expansion is an uncontrolled change. The system is not in thermodynamic equilibrium during the free expansion. Also, this free expansion cannot be plotted on the PV diagram. Only its initial state and final state can be plotted. But during the free expansion cannot be plotted on the PV diagram. The example of a free expansion is when a balloon is punctured suddenly, or when a tire is punctured. The air suddenly moves out and there is no displacement, like there is displacement of the piston or any other surface. Now here there is no displacement in this free expansion when the air is moving away. So such expansion is called as the free expansion. Now in this chapter there are many more points, but due to the COVID-19 pandemic, all the points are related from the syllabus of this year, 2021. So this was the last point. We will be discussing some problems, some unsolved problems from the book now.
A gas contained in a cylinder fitted with a frictionless piston expands against a constant external pressure of 1 atmosphere from a volume of 5 liters to a volume of 10 liters. In doing so, it absorbs 400 joules of thermal energy from its surroundings. Determine the change in internal energy of the system.
Now, given in the unsolved problem is gas inside a cylinder which is fitted with a piston which is massless, frictionless, movable piston, and this the pressure outside is 1 atmosphere. That is 1 atmosphere is 1.103 into 10 to the power 5 Newton per meter square is 1 atmospheric pressure. And it expands. The gas inside the cylinder expands from 5 liter to 10 liters. So the initial volume is 5 liters and the final volume is 10 liters. So now this 1 atmosphere we have converted to Newton per meter square. But this liter, now we want to solve the problem in the SI system. Hence, now we know that 1 ml, 1 milliliter is equal to 1 cc, that is centimeter cube. Centimeter cube. Now I want to convert this liter into proper units, that is meter cube. So 1000 ml, that is equal to 1 liter is equal to 10 to the power 3 ml is, but 1 ml is 1 cc. So 10 to the power 3 ml is 10 to the power 3 centimeter cube. So 1 liter is 10 to the power 3 centimeter cube. Now, since 1 meter is 100 centimeter, so 1 meter cube is equal to 100 to the power 3 centimeter cube. 1 meter cube is equal to 10 to the power 2 to the power 3 centimeter cube. So 1 meter cube is equal to 10 to the power 6 centimeter cube. So therefore 1 centimeter cube is equal to 1 upon, so I take this 10 to the power 6 here, 1 upon 10 to the power 6 meter cube, that is 10 to the power minus 6 meter cube is 1 centimeter cube. So now this 1 centimeter cube is 10 to the power minus 6 meter cube. Now 1 liter, that is equal to 10 to the power 3 centimeter cube is equal to 10 to the power 3 into 10 to the power minus 6 meter cube. So that is equal to 10 to the power, this is 3 minus 6 is minus 3. So minus 3 meter cube. So 1 liter is equal to 10 to the power minus 3 meter cube. So for this 5 liter, I will write 5 into 10 to the power minus 3 meter cube, and this 10 liter I will write 10 into 10 to the power minus 3 meter cube. So I have converted liter into meter. Now the work done by the gas in expanding from 5 liters to 10 liters is W is equal to P dV. That is W is equal to P into V2 minus V1. So W is equal to P, that is 1 atmosphere 1.013 into 10 to the power 5 into V2 is 10 into 10 to the power minus 3 minus V1 is 5 into 10 to the power minus 3. So 1.013 into 10 to the power 5. This is 10 to the power minus 3 we can take in common. So we write into 10 to the power minus 3, 10 minus 5. So this is 1.013 into 10 to the power 5 minus 3 into 5. So answer is 5.065 into 10 to the power 2. We multiply 5 by this, 5 by 1.013 and 10 to the power 2 we take here. So we get here work done is 506.5 joules of work is done. So now asked in the problem is, it is said that when during the expansion from 5 liter to 10 liter, the system absorbs 400 joules of thermal energy from the surrounding. So how much is the change in the internal energy? So from the first law of thermodynamics, we have Q is equal to delta U plus W. So Q is 400 joules. So 400 joules is equal to delta U plus W, which is we have found as 506.5 joules. So delta U is equal to, we shift here on the left hand side. So we get 400 joules minus 506 joules. So delta, we rearrange it again. So we get delta U is 400 joule minus 506.5 joules. That is 1 minus of 106.5 joules. So the change in the internal energy, the decrease in the internal energy is 106.5 joules. The answer given in the book, it does not have minus sign.
A system releases 125 kilojoule of heat while 104 kilojoule of work is done on the system. Calculate the change in the internal energy.
Given in the problem is, there is a system which releases 125 kilojoule of heat. Now since the system is not taking the heat, it is giving away the heat, it is releasing the heat. Hence, we have to take the heat, Q is minus 125 kilojoule because it is releasing the heat. And the system does, and work is done upon the system. And in the given in the problem is, work is done upon the system. Work is not done by the system. When the system does the work is positive. When work is done upon the system, the work is negative. Now, work of 104 kilojoules is done on the system. So, work done is minus 104 kilojoule. Now, they have asked us to find the change in the internal energy. So, according to the first law of thermodynamics, Q is equal to delta U plus W. So, now Q is minus 125 kilojoule, that is equal to delta U plus 10 plus of minus 104 kilojoule. So this is minus 125 kilojoule. This is equal to delta U minus 104 kilojoule. So taking 104 here and rearranging, delta U is equal to minus 125 plus 104. That is equal to minus 21. So delta U is equal to minus 21 kilojoule is the answer. In the book, minus is not given, but the answer is, the change in the internal energy is minus 21 kilojoule. Internal energy of the system has decreased by 21 kilojoule. So in the problem, it is given that an ideal gas is taken through an isothermal process. So since the process is isothermal, so temperature is constant. That is, the change in temperature delta T is equal to 0. And since there is no change in temperature, there is a constant temperature. So the change in the internal energy will also be 0. That is, U is equal to 0, because the process is isothermal process. Now this gas which is taken through isothermal process, it does work on the environment. So since the gas is doing work, the system is doing work, so the work will be positive. So its work done is 2000 joule of work. So but it is plus 2000 joules. Now they have asked us to find how much heat is added to the system. So according to the first law of thermodynamics, Q is equal to delta U plus W. Now, since they have asked us to find Q, delta U is given 0. Work done is plus 2000 joule. So, Q is equal to plus 2000 joule is the heat added to the system. Thank you.